Derpity derp 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 derpity derp 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 derpity derp 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 derpity derp derp derp.
Are you okay? Here, have a bandage.
Why is there silver in this?
Don't you remember in SSP chemistry? There's silver nanoparticles.
Nanoparticles? Someone say nanoparticles.
Who are you? What are nanoparticles?
Well, nanoparticles are particles that are like 1 to 100 nanometers in size. Yeah. And a nanometer is a billionth of a meter, so that's pretty small. And that gives nanoparticles meaningful properties. See? Like when a red laser beam passes through a sample of nanoparticles, we can see the path of the laser within the vial as a thick red line of light. This demonstrates the Tyndall effect, which is the scattering of light caused by colloidal particles, that is, particles approximately 1 to 1,000 nanometers in size, so on the nanoparticle scale. Because the wavelengths of visible light are similar to the size of the nanoparticles, it can't travel in straight lines and instead collides with the nanoparticles and becomes scattered, making the beam of light visible. Compare this to how a laser passes straight through a solution of yellow food dye. You can see the light at the other end, but you can't actually see the light passing through the sample itself. This is because the solution of food dye have particles that are too small, so they allow light to pass straight through.
How do we make this?
Don't you remember how we made them in the lab?
Blue. Turn blue. It turned blue because I made it turn blue. Yeah. This is not chemistry. This is magic. Magic.
Yeah, it was magic.
Yeah, no. See, actually... Nanoparticles can be prepared using physical, chemical, and biological methods. You would have made nanoparticles by reducing the silver cations to silver atoms using sodium borohydrate. This is referred to as the chemical reduction method. In the chemical reduction method, silver cations are reduced to silver atoms. This process is called nucleation. The silver atoms will agglomerate into tiny clusters that form colloidal silver nanoparticles. If this process isn't controlled, the tiny clusters will get bigger and bigger until the particles are no longer considered nano-sized. To prevent this from happening, a capping agent is used which stabilizes the growth of the particles. You use trisodium citrate as a capping agent. So here's how it works. Trisodium citrate forms an electrical double layer. One layer complexes with the silver nanoparticle, and the other interacts with the silver ions. This causes repulsion between nanoparticles. This type of stabilization is called electrostatic stabilization. By controlling the ratio of reducing agent and capping agent, you can also control the size of the nanoparticle. Controlled growth of nanoparticles can produce a wide range of shapes, like planar shapes, cubes, and prisms. In the lab, you manipulated the shapes of nanoparticles using hydrogen peroxide. The opposing actions of hydrogen peroxide oxidizing silver back to silver plus, with the sodium borohydrate reducing your silver cations back to silver, form an equilibrium that creates the prism shape. The shape can be resolved using atomic force microscopy.
We make those pretty colors. Let me think.
Hey Mohammad, this is your subconscious. Funny you don't normally sound like this when you're speaking. Anyways, let me try to explain you the science behind nanoparticles.
What's this white sheet?
Oh, it's your mind. You know, it's pretty blank.
Whoa, whose hand is that?
It's Wendy's.
Hello.
How many subconscious voices do I have?
Shush, Mohammad.
Now, the color of the solution depends on the size and shape of the particle. When light hits the surface of the silver nanoparticles, its free electrons oscillate back and forth due to the excitation of the light at a specific wavelength. This process is known as surface plasmonic resonance. The oscillation results in unusually strong scattering and absorption properties. A specific size silver nanoparticle will absorb a specific wavelength of light, and as a result, this causes the observer to see the color that is complementary to the color absorbed. When light is shined through the silver nanoparticles, for instance, our UV-Vis spectroscopy data, it can be seen that there is a maximum absorption peak at 532 nanometers, which corresponds to the color green. Since green is absorbed by our nanoparticles, the color red will be seen.
Well, I remember now they have antibacterial properties, so they're used in band-aids. They are used in composite fibers to make threads stronger than steel. They're used in molecular tagging, and they also are used in superconducting materials, and that's why nanoparticles are important.